Alright, proof by induction, it seems difficult, but trust me, it is actually the freest marks you can get in A-level further maths, and I am going to show you how. I found this question the other day. Prove by induction that for all positive integers n, this is true. I'm not reading that all out loud. Okay, so what do we do for proof by induction? First of all, we do the base case. Base case is p of 1. When n is equal to 1, we get the sum from 1 to 1 of this, right? Which is just 1 over 1 times 1 plus 1, which is 1 over 2. That's the left-hand side. And the right-hand side is going to be 1 over 1 plus 1, which is 1 over 2. 1 over 1 plus 1 is 1 over 2, RHS. So that is the base case is true. Now, we need to assume that it's true for p of n. Assume true for p of n. You need to be careful in these questions because they're really strict on the way you word things. You need to be precise. Okay, assume true for p of n. The sum from r equals 1 to n of 1 over r times r plus 1 is equal to n over n plus 1. Now, let's examine p of n plus 1. Okay, so p of n plus 1 is the sum from 1 to n, 1 over r times r plus 1, plus the n plus 1th term, which is 1 over n plus 1 times n plus 2. So, using our inductive assumption, we know that this is equal to n over n plus 1. N over n plus 1 plus 1 over n plus 1 times n plus 2. So, we now need to add these together, basically. You should know how to do this. You're doing further maths. So, n times n plus 2 over n plus 1 times n plus 2 plus 1 over n plus 1 times n plus 2 is equal to n times n plus 2 plus 1 over n plus 1 times n plus 2, which is equal to n squared plus 2n plus 1 over n plus 1 times n plus 2. This obviously looks familiar. That's just n plus 1 squared over n plus 1 times n plus 2. And we can cancel out one of the n plus 1 terms on the numerator and the denominator to get n plus 1 over n plus 2. That would be our left-hand side. Our right-hand side would be, looking back at what we need to prove, if we substitute in n plus 1, we get n plus 1 over n plus 1 plus 1, which is n plus 1 over n plus 2. LHS equals RHS. So what we have proven is that p of n leads to p of n plus 1 being true. But here is the induction bit. But we know, because we have demonstrated, that p of 1 is true. So that means p of n is true for all n's which are integers greater than 1. Or it just says integers, positive integers, yeah, that works. For all integers which are positive. Okay, part 2. Prove by induction that for all positive integers n, that is divisible by 5. Okay, immediately looking at that, that's a bit scary, right? Like, where do you start with that? But let's follow the same process. So, the base case, p of 1, f of n, is equal to 3 to the power of 6 minus 2 to the power of 2, which is 725, and 725 obviously is divisible by 5. So our base case, we need to write that out actually, base case. Our base case is true. Now, same process, we assume true for p of n. Okay, that should actually be f of 1. We assume true for p of n. So, 3 to the 2n plus 4 minus 2 to the 2n is divisible by 5. Now, let's examine p of n plus 1. So, p of n plus 1 is 3 to the 2n plus 6 minus 2 to the 2n plus 2. So what we want to do in this kind of induction problem is we want to represent it in a form that resembles the assumption. So what we can do is we can take 3 squared out of this, and we can take 2 squared out of this. Let's do that. 3 squared times 3 to the 2n plus 4 minus 2 squared times 2 to the 2n, which is 9 times 3 to the 2n plus 4 minus 4 times 2 to the 2n. So that's looking a bit more like our assumption. What we can do now is let's take out 4 of 3 to the 2n plus 4 and 2 to the 2n. So we have 4 times 3 to the 2n plus 4 minus 2 to the 2n plus 5 times 3 to the 2n plus 4. Okay, and now we're almost done. Okay, so according to our assumption, 3 to the n plus 4 minus 2 to the 2n, that should be 2n plus 4, is divisible by 5. That was p of n. So that means 4 times 3 to the 2n plus 4 minus 2 to the 2n is divisible by 5. So that bit there is done. That's divisible by 5. Now, 5 times 3 to the 2n plus 4 is obviously divisible by 5. It's got a factor of 5 right there. Which means 9 times 3 to the 2n plus 4 minus 4 times 2 to the 2n is divisible by 5. Okay, so we are almost done. We just need to do the conclusion. You need to be careful. Like I said, this is normally worth 2 marks. Okay, so we have shown that p of n means p of n plus 1 is true. But p of 1 is true, as we've demonstrated with the base case. So p of n is true for all positive integers. And that is how you do a proof by induction. That was a quick taster of how we teach in NABLA tuition. We make sure that you understand the entire process, not just memorizing procedures, but actually understanding what you're doing. If you want to book a free 30-minute session, head over to nablatuition.com or email us at contact@nablatuition.com. Thank you for watching.